In this video, I'm going to go over the 5.0 Chem final exam practice quiz that covers solutions. So this first question here, the blank does the dissolving and the blank gets dissolved. So this is just terminology here. The solvent does the dissolving and the solute gets dissolved. The other way you can think about it is the solute will end up in the same phase as the solvent. Right, so sodium chloride, if you dissolve that in water, sodium chloride is a solid, but when you put it in the water, everything ends up in the aqueous phase. So the solute, which was the salt, got dissolved in the solvent, which was the water. The solvent is always in a greater amount than the solute, and that ends up being false. It's usually the case that you have more solvent than solute, but some solutes have such a high solubility that you can actually have a greater amount of solute than solvent. So it's really just this word always that's kind of throwing it off. What will increase the rate of dissolving? And now this is talking about how fast a solute is going to dissolve. It's not talking about necessarily getting more to dissolve, it's just getting it to dissolve quicker. And anything you do to increase the interactions between the solute and the solvent will do it. So increasing the temperature. The kinetic energy is going to increase, so things are going to be moving around faster, so they interact more. Stirring it will do the same thing, cause more interaction. Crushing the solute increases the surface area, so that will increase the rate. And adding a catalyst makes that dissolving happen faster. So all those things actually do it. Alright, now this is asking for the solubility chart. What is the solubility of potassium nitrate at 30 degrees Celsius? Now I ended up printing up one that doesn't have as much stuff on it, so it's a little easier to read. So we're talking about potassium nitrate at 30 degrees Celsius. So what I would do is, well, we have to figure out potassium nitrate is this line. So I'll just outline that a little bit, just to make that obvious. And it was at 30 degrees. So we find 30 degrees, you go up to that line, so it's right about there, and it looks like it's just below 50. And so let's look at our options here, and it looks like we would go with this 48. Now, it says per 100 grams of water, and that's an important part you want to remember when you're looking at these solubility charts. This one says per 100 cubic centimeters, which is the same thing, really, right? So this is basically saying per 100 milliliters of water, right? So if you change the amount of solvent, you would actually get a different amount of solute to dissolve. So you want to pay attention to those things. Now this one's asking us for another solubility chart, and it's asking us about sodium nitrate. And it's saying what type of solution will be formed if you dissolve 120 grams of sodium nitrate in 100 milliliters at 40 degrees Celsius. Alright, so when I printed this up, it actually had sodium nitrate on there too. And what it was asking us for is at 40 degrees Celsius. So right here I'm going to go up, and this is the line we're looking at. Now this tells us, though, again, it's in 100 milliliters of water, so that's good. We don't have to worry about that. But it's saying 120 grams at 40 degrees Celsius. So we go up to 40, we'll go from 40 degrees Celsius up to 120, which looks to be right there. We're above the line. So if you're above the line, that is supersaturated. Right on the line is saturated, and anything below the line is unsaturated. So that would be a supersaturated solution with those criteria. Alright, now we're going to get into a little bit of math with this. How many grams of bromine are needed to prepare 0.50 liters of a 0.0100 molar solution of bromine in water? You have to pay attention here that bromine is diatomic. So bromine off the periodic table is 79.9, but since there's two of them, we have to remember to multiply that by 2. And for some reason it seems like sometimes with students, when something is diatomic, they forget about the 2. Right? You have to multiply it by 2. Now, if we're talking about molarity, the equation for molarity is moles per liter, which gets abbreviated to N over L, but you could write it as moles per liter. Well, I guess technically it's N over V. All right, now it's asking for grams, and grams isn't given right here. So what we have to do is rearrange it for moles, and then when we get our answer in moles, convert that to grams. So when we rearrange this for moles, it's volume times molarity. And what we end up having is the volume is in 0.500 liters. A lot of times with molarity, instead of N over V, I think about it specifically as moles per liter. We need the volume in liters, and we need the amount in moles. Now the good thing is that the volume was given to us in liters. So we don't have to do anything with that. We could just put that in there, 0.500 liters. And now the molarity is 0.0100. Instead of writing a capital M, I'm going to write it as moles per liter. Because now you see that the liters will cancel out, and what you'll be left with is moles. And when you multiply that out, you get 0.00500. I'm just keeping the significant digits the same. Moles of Br2. But it's not asking us for moles, it's asking us for grams. And this is where this 159.8 grams per mole is going to come in. So we multiply that answer by 159.8 grams per mole. The moles will cancel out. You end up getting 0.799 grams, rounded off to 3 significant digits because that's what we're working in this problem. And we end up getting that answer. Just remember, bromine's diatomic. It's easy to miss that part. Number 7, what is the molarity of a solution formed by mixing 10.0 grams of sulfuric acid with enough water to make 100 milliliters of solution? Remember, molarity is moles per liter. So there's two things going on here. We don't have moles, we have grams. And this part's easy to fix. The 100.0 milliliters, we'll have to convert that to liters. Right, so we could do that right away. 1000 liters. But we have to get the moles part. So if you're talking about sulfuric acid, remember it doesn't say hydrosulfuric acid, so it's not binary. You're going to need a polyatomic ion, and this ending in IC is telling you that you're going to use sulfate. So what you get is H2SO4, because sulfate is a -2, hydrogen +1, so when you crisscross you get that H2SO4. We're going to take that 10.0 grams of sulfuric acid, and we are going to convert that into moles. So we have to get the molar mass of sulfuric acid. It's going to be 1 mole up top. So for this molar mass, oxygen is 16 apiece. There's 4 of them, so that's 64. Sulfur is 32.1. Hydrogen is 1 apiece, but there's 2 of them, so that's 2.0. So when you add all this up, you get 98.1. So it's going to be 10 grams divided by 98.1 grams, and that is going to be 0.102 moles, which is what we will plug in up here. Now we have those units of moles per liter, which is good because that's what we're looking for molarity. So when you divide this, what you end up getting is 1.02, and you can either write moles per liter or you can write M. It doesn't really matter which. The multiple choice options in this case just have a capital M because that's what people usually go with as the abbreviation, 1.02 molar. Alright, now this last one, a solution. Pick all that can apply. Well, a solution can be a solid, liquid, or gas. Now this one can be either homogeneous or heterogeneous. Well, solution by definition is homogeneous. It cannot be heterogeneous. If it's heterogeneous, it's not a solution, so that one's out. Solution is a homogeneous mixture. That really is what I just said. And it's always in the liquid state. That part's wrong because you can have alloys which are solid, or you can have solutions that are gases. And so it's those two there. And that is it.